this is the last section in chapter 7, 7-4. And what we're going to be talking about is the normal probability distribution, okay? So we'll look at the normal approximation to the binomial probability, all right? Now, binomial probability, if you think about it, we did this, I think, chapter 6, right? Or was it first sections in chapter 7? I can't remember. But we've done a binomial probability, right? And it's a fixed number of trials. It's two outcomes, yes or no, or, success or failure and everything. But we're going to learn how to normalize, use a normal approximation on a binomial probability distribution, okay? So that's the whole thing with 7-4, all right? And we get done, it should make a little bit more sense. So the criteria for binomial probability experiment, the experiment is performed in time, so there's a set number of trials, right? Independence means that the outcome of one trial will not affect the outcome of the other. For each trial, there are two mutually exclusive outcomes, right? Success or failure. You either have one or the other. And then the probability of success, P, is the same for each trial of the experiment, all right? Now, again, that's a refresher of binomial probabilities. And we did that, I think, in chapter 6. All right, for a fixed P, as the number of trials in a binomial experiment increases, the probability distribution of the random variable X becomes nearly symmetric or bell-shaped. And we talked about that. You increase the sample size, the shape itself becomes more bell-shaped, no matter if it's skewed left or skewed right. We saw that, again, those types of graphs were in chapter 6. And as a rule of thumb, N times P times 1 minus P, if it's greater than or equal to 10, then you can do a normal approximation on the binomial probability, okay? So I want to just kind of, let's see up here. All right. I want to talk about N is the sample, right? Sample size. P is the success. And then the 1 minus P, we're going to say that's Q, right? So I'll refer to Q several times, but that is just 1 minus P. And that's basically the failure, right? The percentage of failure. You either have a success, and then the 1 minus P will be how much percent is failure. So if this N times P times Q, right? So really it's N times P times Q. If it's greater than or equal to 10, right, and Q is 1 minus P, then we can do a normal approximation on a binomial probability distribution. So some formulas you need to make sure you get or understand from here. Let's put some highlighters. Mu of X, or the mean, is N times P. And then the standard deviation of X will be N, the square root of NP. And of course, it's really this, the square root of NPQ, right? All right. So I'm going to use Q, and it's 1 minus P. All right. Any questions about that? So looking at this, if you got a binomial probability, we looked at it on a histogram, right? We plotted the binomial distribution on a histogram, and they're bars, okay? But if you do a normal approximation, you put a normal curve over that, you can see where this portion of that bar is not taken into account. And then you can also see where the A is not on the outside or left or right perimeter, it's in the middle. So what you're going to do is, for an approximation, normal approximation of a binomial probability, is you're going to go plus 0.5 or minus 0.5 from A. Okay. Now, it depends on if you want greater than, less than, or greater than equal to, or less than equal to, or between things. So, and they've got it here, A minus 0.5 less than X less than, or A plus 5, right? So we're looking at a half, either half above or half below, okay? In doing that, it allows the normal approximation to be very, 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 very close to the binomial probability model, okay? Because what it's going to do now is it's going to take, like if we were looking at this, then we'll be looking at the minus 0.5 of that, and then the plus 0.5, the plus of that, right? So, for example, let's say, let's kind of erase that, and I'll show you what I'm talking about. If this was 17, if A was 17, so we would be really looking at 16.5 all the way to 17.5 if we were to do a normal approximation of binomial probability, okay? And that's to take into account this. Because if you only do right here, then you're missing half of the binomial probability. You have error there, okay? So here's another curve or graphical depiction of probability of X less than equal to A. So if it's less than equal to A, let's say A, or the X, right, is 16. I wouldn't just pick 16. It would be from negative 1e 99 up to 16 and a half. You know, if you look at it from a normal cumulative distribution function, right? So, and we would normal CDF, and then we would say the mean of X and then the standard deviation of X, right? That's how that would be typed in, okay? Because we want to make sure that we get the full bar of 16, because 16 is in the middle, all right? So let's look at another one. On this one, it's things greater than equal to A. Greater than equal to A, it's going to, you know, if this is again 16, so we'll be going to, you know, 15.5, right? So we would do a normal CDF, right? Because we're doing a normal approximation of a binomial probability. We would do, again, this is like a lower bound, upper bound. So the lower bound would be 15.5, comma, 1e 99. That would be the upper bound up here, right? And then we would take the mu of X, or mean, and the standard deviation of X, right? Okay, that's how we would do that. And it would give us all this area right in here, okay? All right, any question? That is basically, it's 1e 99. It's when you do a normal CDF, the positive 1e 99 is infinity, right? Upper bound is infinity. And on the previous one, we did the lower bound down here, right? Down here would be negative infinity. Well, how do you put that in as a lower bound? Negative 1e 99. Now, how do I get the e? How do I get scientific notation? Well, if I go to my calculator, if I were to do second and then the comma, second and the comma is right above the 7 button. That gives me a double E, which allows me to put in the, that's really like the times 10 on a scientific notation, and you just put your, you know, exponent, right? So, all right, we're going to do some, and you're going to be able to type it in. So I'm just kind of showing these out, how it's written. Now, what happens if it's between right? If they want between, um, you know, like if this is 16 and that's 18, well, if you look at this, then this right here is really going to be 15 and a half. And this right here is really going to be 18 and a half, okay? So when you do a normal approximation on a binomial probability, again, remember that it's actually a bar, right? I mean, if you looked at this, uh, binomial probabilities are basically histogram, right? They're the little tall rectangles. So when you do the half, it gets a closer approximation, okay? So we do this, normal CDF, right? The lower bound would be 15 and a half. The upper bound would be 18 and a half. And then you use your mu, or mean of x, and then your standard deviation of x, right? So that's kind of how you're going to type it in to find that area or that probability or that proportion, right? So again, just wanted to point that out. Here's a really good, you know, it says for correction for continuity, the correction for taking a bar and making it into a curve, you know, because a normal approximation is a curve and a binomial is the box. It's the rectangular box, right? It's the histogram. So here's a chart. You know, if the probability is equal to A, then we've got half below it and half above it, right? So we have to get the left side of the bar and right side of the bar at that particular point. If things are greater than and equal to, then it's A minus that, right? If it's just greater than, then it's A plus it. You would not do the left because it would not include that particular point, right? Less than equal to would be the value plus 0.5, and then if it's just less than, then it's A minus that. And if you draw it out, and we'll show you how to draw it out, kind of look at it, it makes a little bit more sense where you add and subtract 0.5s, right? So, but this right here is an excellent, I snagged this off the video, and I like this, but they really should have done this, right? For this, right? But the representation, he couldn't, or I say he, um, they couldn't do that. So I thought this chart, you know, is all five combinations really. So I thought that was a really good reference to use. So let's kind of look at this example. It says, according to the Experian Automotive, 35% of all car owning households have 3 or more cars, right? So we're going to do this by hand, and then we'll also do it by the calculator, all right? Because I want you to be able to see what it looks like doing a calculation by hand. So in a random sample of 400, right? So our n is 400. What is the probability that fewer than 150 have 3 or more cars, right? So basically, we are looking at the probability of x being less than 150, right? Less than 150. Now, the probability of success on that is 0.35, right? So the Q on that, the failure, the probability of a failure, if the success is 0.35, then the failure would be 1 minus that, and that would be 0.65, right? Again, let me write this right here. It is 1 minus P, right? That's how we got that. Okay, so I got people's chats. So anyway, NPQ. So let's find mu. The mu of x, which is the mean of x, is n times p. So that would be 400 times 0.35, right? Which would equal 140. And then if we want to find the standard deviation of x, right? Then that's NPQ, right? It's just not NPQ, it's the square root of that. So if we look at that, that would be the square root of 400 times 0.35 times 0.65, right? And that's going to give me 9.5394. Okay, so I've got, let me change colors. So I've got the mean is being 140 of X, and then the standard deviation of X is 9.5394, right? Those are all calculations you can do by hand. Now, it shows that to find the Z, right? Z, zeta, Z, not zeta, Z is less than, so let's see. If it's fewer, so fewer than 150, so let's kind of draw that, right? And I'll show you what I'm about to do. So here, this is 140, right? Oh, cuss. Okay, this is 140, and if I go and I'm wanting basically less than 150, right? So I'm here at 150, all the way over, right? So if you look at the bar, I'm supposed to go one below it, right? So the A value that I'm needing is 149 and a half, because it's not including 150, right? It is less than 150. So if it was including 150, then I'd have to go 150.5, right? To make sure that, you know, that 150 was there, but it's not including. So I'm really using 149 and a half. So if I look at this, it's 149 and a half minus 140 over the standard deviation, right? And this is the mean. I'll just type this out, and then I'll put what things are. Okay, so you get a Z that is basically less than 0.9956, right? So where do I go to go find this? Well, you've got to go to a table, right? So if we're looking at the table, we should be able to go 0.995 and get, well, let me do this real quick before we move off this. Here's the X value, right? And then here's the mu of X, and then this right here happens to be the standard deviation of X. So let me make sure I've got, yeah, that would be normal curve. So yeah, I don't want that, shoot. That would be 7, for normal distribution, I'm looking at 0.99. Is 0.9959 is 83891, right? Y'all see this? 0.99, right? So you put 0.83891, okay? Which is basically, if you rounded it, it would round up to 80, you know, if you 0.8389, right? It's the area underneath it. Now, that's, we've got 0.9959, right? And we're just at 0.99. So you can take it from a table, and that's fine. It's not a problem there. But you can also, I prefer you to do it on the calculators. So here's it on the calculator. If you type in Let me extend this. Normal, CDF, right? Cumulative, because we're doing everything here, right? So we need a lower bound, and the lower bound would be negative 1e 99, comma. The upper bound would be 149.5. The mean would be 140, and then the standard deviation would be 9.5394, right? So if you type that in, you actually get 0.8403, right? And we were like, what, 8399 something, right? 0.8399 with the table, right? Let's go back over here. 0.8389, right? 0.8389. Table gave us 0.8389, right? And if you do it on a calculator, it's 0.8403. So let's do it on the calculator real quick, because I want you to be able to see that on the calculator. And I prefer you to do it on the calculator, right? Because that way you don't have to work on, go back to the table and all this other stuff. And two, you don't have to do all these calculations, right? The calculator will do it for you. You have to find the Z, the ZEB, right? And all that. So if we go, let's go second, VARs, right? And we're doing a normal cumulative distribution function. Now, mine comes up at the lower is already at negative 1e99. So we'll hit enter. Upper is going to be 149.5, right? 149.5. Now my mean, we said our mean was what? 140. That was n times p, right? And then standard deviation for this one happened to be 9.5394, right? Yep. All right. Now enter, paste, and then enter. And it comes out to 0.8403. Okay. So it's a lot easier to just calculate the mean, calculate the standard deviation of it, and then use the normal cumulative distribution function to find the area underneath it, right? So that's no. If you make sure that you're hitting number 2 and not 1. Yeah. What kind of calculator do you have? And you're actually hitting selection number 2, like on the keyboard, on the calculator, number 2, not scrolling down and hitting enter, just hit 2. Oh yeah. Go second mode, get out of that, and then go back in and see what the first one gives you. It sounds like it may have had a install. Is it new? Yeah, I'd take it back. Um, yeah. All right. So that's how you type it in. Okay. So that's there, and that's how you do it by hand. So you could actually see it. Does the 0.5 below it make sense while we're at 149.5 and not at 150? Are y'all good with that? Do you understand why it has to be below it by half? Okay. So hopefully do. The video I put up is really, really good on that. So you can see that if you need to. If you go to the next one, I like to work it out. They've done it there as well, right? So you've got it both ways. Now this third one, or not third, really it's part B. The probability that's going to be greater than equal to 160, right? At least. So really what you've got, if you look at this, and we said we got a mean, right? If you look at this, the mean happens to be at 140, right? Isn't that our mean that we calculated? And this says 160, right? We kind of do that. This is 160. Well, we are wanting, including at least 160, have probability to have at least 160. So 160 is really included, and it's our lowest spot. So we're wanting all of this. So if you think about this, histogram bar is really doing this, right, at 160. So I need really that so that I'm getting the full 160. So that's why it's minusing it. That's why this is 159.5. And if you draw that little shape, the little normal curve, and put it and kind of see, do I include it? If I include it, then I got to, go back to the left, right? And if I didn't include it, if it was just greater than, right, 160, then it would be 160.5, right? So just kind of look at that and draw it in and make a little bit more sense. And then you could do, like on this one, normal CDF, right? And I'll write it out. The lower bound would be 159.5, right? Your upper bound would be 1E99. Now that right there, the E is second comma button, right? Right, second comma button. And then, of course, 140, and then our standard deviation happens to be 9.5394, close parentheses. And again, this on the calculator, it gives you, now they're looking at the table, right? On the calculator, it's giving you this, right? So tens, hundreds, thousands. So 2 thousandths difference, right? And if you look at that, that's not bad. Yeah, yeah, I don't know how much I'm gonna be able to help you because I can't see it. Does that make sense? It's hard to, well, you probably gonna have a test before then. I'd just take it back. I'd just return it and say, this is faulty, this isn't doing right. And they'll replace it. Oh my, okay. Well, um, yeah, yeah, it's gonna stay there until it's wiped out, right? So you're gonna have to typo with that. But just this is how you do it on this, and we can talk a little bit more about it that later. But when you do it by the calculator, you get 0.205, right? Not that 0.0205. I left out a zero there. Okay. All right. So that's really all of the example problems that we're doing. This the next couple of problems are actually homework problems, right? So the first thing is, in order to do a binomial experiment with n trials and a probability of success being p, this n times p times, it's really n times p times q, right? Which is n times p times 1 minus p, has to be greater than or equal to 10. If that is greater than or equal to 10, then I can do a normal approximation on a binomial probability. Okay, I can treat that curve, right? And then, of course, what's the calculation for mean, the mu of x, and then the standard deviation of x. These are just regular plug and chug. Well, I shouldn't say plug. They're just formulas, right? So if we're looking at this particular problem, okay, we're looking at this particular problem. It says, okay, compute the binomial probability, right? It said a binomial probability. Then determine whether the normal distribution can be used to estimate this probability. Can we do it with a normal approximation? And then if so, approximate it using the normal distribution and then compare the results. So what we're going to do is, first off, we've got to do a binomial PDF, right? So we're going to do a binom PDF. And the reason we're doing a PDF is this is exactly 29, right? exactly a probability distribution, the binom PDF is for exactly 1 point, right? Exactly 1x. If we had something that was up to that, right, then we would do a cumulative, right? So if you think about when we did binomial probabilities, there was 2 functions that we used, the binomial PDF and then the binom CDF, which is cumulative. It takes everything from there to the left, right? So this is particular thing is an equals. So what we've got is, okay, for a binom PDF, it wants to know your n, right? It wants to know your p, and then it wants to know your x, right? That's what it definitely needs. So what we're going to do is we're going to say binom PDF is 44, right? Comma 0.6, comma, and then 29, right? And when we do that, and we'll do it, so let me go here. We're going to do second vars, and we'll have to go all the way down to A or B. I can't remember which one it is. A is a binom PDF. So hit enter. The number of trials is 44, right? That's the n, 44. The probability for success on this particular one happens to be 0.6, right? The x value that we're wanting, and only the x value, is 29, right? So we type that in, we hit paste, boom. It tells us that we got 0.0 0.091, right? Okay, now that's what's going in here, 0.0910, right? It's going in right there. Okay, so that's the binomial probability for 44, n of 44, success of 0.6, and x, exact value of 29. Okay, now if we go to the next page, which really has the rest of the problem, so it has this, right? So here's the 0.0910 that we just calculated, right? We just calculated that by doing a binom PDF, right? Can the normal distribution be used to approximate this probability? We've done it with a binomial probability distribution, but can we do a normal? Well, in order to do a normal, it has to do this, right? N times P times Q. Well, it has to be greater than or equal to 10. Well, the N is 44, the P is 0.6, the Q, which is the failure, right? The 1 minus P is 0.4. And that has to be greater than or equal to 10. And when you do that, you get 10.56. And is that greater than 10? It is. So yes, we can do a normal distribution because n times p times 1 minus p, which is actually the q, right, is greater than 10. So that's why selection B is there. Okay. So any questions on that? All right, so down here, they're saying, okay, do the approximate P of X using a normal distribution, right? So we've got to find 2 things. We've got to find the mean, right? The mean of X, or mu of X, which is N times P, and that's going to be 44 times 0.6, which is going to be 26.4, okay? And then we're going to have to find the standard deviation of X, right? Because we need that. That calculation is going to be the square root of N times P times Q, right? Which would be the square root of 44 times 0.6 times 0.4, right? That happens to be 3.2496, okay? So these 2 calculations have to be done in order to do a normal distribution of a binomial probability. Guaranteed, boom, got to have those, right? But that information will be given to you, all right, in the problem, the N, the P, and then you can find the Q, which is 1 minus P. Now, from this, we can do a normal CDF, right? Normal cumulative distribution function. Now, exactly, let's kind of look at this. Exactly, you got to draw this bell curve, right? And again, mine is just rough bell curve, right? So do this, boom, the mean is 26.4, right? There's the mean. Now, we're looking for exactly what? What did it say? Exactly 29, right? So when you do this, you're going to, it's up here, right? So that's 29, but exactly it's going to, you know, we're looking at, this is the curve, right? So if we're looking at the box is doing this, right? For a binomial probability. So we're really looking at 28.5 up to what? 29.5. One exact point, we're going a half below and a half above it to make sure that we're getting the full box, right? Okay. So when we do this, the normal CF says, okay, I need a lower limit. Well, that lower limit is going to be 28.5, right? And then we're going to say the upper limit is 29.5. And then we've got a mean of 26.4, right? If I write that a little bit better. And then a standard deviation of 3.2496. Now, you need to go out to about 4 or 5 decimal places on your standard deviation if you don't want to have to put this square root of 44 times 0.6 times 0.4. At least 4. It'd be great if you went 5, but anyway, because this said 4 and some things, 4 is fine, right? But we're going to type this in, and we should get 0.0890. Okay, so let's go type it in so you at least see how we do this. Second, so we're doing a normal, right? Cumulative, right? So we got a lower bound, and that lower bound is 28.5. The upper bound is 29.5. The mean is 26.4. The standard deviation of X is 3.2496. Hit enter, paste it. And if I do that, I get 0.089, right? So the next question that they ask us is this. They go, what is the difference between the two probabilities, right? So for me, I'm just going to highlight it. That'll bring the 0.09 minus, right? Minus. And if I go answer, which would be second negative right there, if I hit that, then I see that I have a 2,000ths, right? 0.002, 2,000ths difference between it, right? So, and that's one of the questions, right? So 0. Okay. So this right here is 0.0020, right? Round to 4 decimal places, so it's a 2,000ths difference, right? So if you change that to a percent, you're really looking at 0.2, 0.2% difference, right? And that's negligible. Okay, so it's a really, really close approximation, right? So there you go. Any questions on that one? This particular problem had a binomial probability that we had to do, and then we did the normal approximation on it, right? It's an exact number, so we went half below it and half above it, right? For the normal, to make sure that we got the approximation better. All right, so let's go look at the next problem. No, that's it. Okay, so that's really with the problems, the example problems that we did. in the lecture portion plus this, that's really all they've got. They're going to really use this table, okay? But if you draw it out, if you draw a bell curve out and put where your mean is and put where your point is, does it include that point or not, right? So if it includes that point, then you're either going to add or subtract 0.5 of it, depending upon if it's below or above, right? So if you look at this, this is probably the most beneficial slide out of the whole thing. So if there was something that I was going to write down or have so that when I do a normal approximation of a binomial probability, this is what I would do, okay? And it's got to have the 0.5s because you're below and above that particular point, because the binomial probability is a histogram, right? It's a box, and you're normalizing it with a curve. So you're trying to get as much area in there to be able to get a really close approximation. All right, so that's all of 7.4. So that 7.1, 7.2, and 7.4, I think that's a test by itself, right? Okay. So just make sure you're aware of that. Let's go on to 8.1. That's also where we were looking at tonight. We're going to look at distribution of the sample mean, right? We're going to describe the distribution of the sample mean compared to a normal population, right? We're going to describe the distribution of a sample mean to a non-normal population, because those are the learning objectives that we should be able to do. Now, what the heck does it really mean? So statistics such as X bar or random variables, since their value varies from sample to sample, right? As such, they have probability distributions associated with them. In this chapter, we focus on the shape, the center, and spread of statistics, such as X bar. So the sampling distributions of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. So the sampling distribution of the sample mean, X bar, is the probability distribution of all possible values of the random variable X bar computed from a sample size n from a population of mean and a standard deviation. Okay, so it's a lot of theory there. Okay, so first thing is, and it'll make sense as soon as we get into this. Okay, it's a lot of theory we have to go through. Step one: obtain a simple random sample of size n, right? And then compute the mean. And assuming that we're sampling from a finite population, repeat step 1 and 2 until all distinct random samples of size n have been obtained. So that's how we're going to do the sampling. Now, sample distribution of the sample mean with a normal population, right? We look at this. Mean is 2.46, and standard deviation of that, approximate mean. The data, the slide show represents the sample means of 200 random sample size n equals 5, right? So there's a table that really goes to this, and if I'd have put it on here, it would have made a little bit more sense, but I didn't. But what I want to show and really make a reference to would be, yeah, there we go. So here's the histogram of it, right? The standard deviation of sample mean is 0.0086, and we're going to calculate that, right? So what we're basically doing is the mean of the sample is going to be equal to the mean of the population, and then we're going to have to calculate the standard deviation of it. Okay, so that's really what we're going to do now. And we looked at this back in what effect does N, meaning the number of samples that you take on it, what role does N, the sample size, play in the standard deviation of a distribution of a sample mean? The more or the greater N is, the smaller the deviation, right? So as the sample of as the size of the sample increases, the standard deviation of the distribution of the sample mean decreases, right? So what does it really look like? So if we take something like this, right, here, and that's the population, we're going to be looking at something like this, okay? Do you see how the data is more grouped in the green compared to the blue? Okay, so when you take that, as the sample size gets bigger, the standard deviation, the spread, the variability of it is going to decrease, right, on the sample mean. That's really what it's saying, all right? So we go back to this. After approximating the sampling distribution of the sample mean by obtaining 200 random samples of size N equals 20 for the population, the weights of the penny minute after 1982, the mean is 2.46 and the standard deviation is 0.2, right? So the mean for the 200 sample mean for N equals 20 is still 2.46, but the standard deviation is now 0.0045. Okay, so, and they say, why did it change? Okay, well, the reason why it changed is this: the standard deviation of X, right, for a calculation is going to be the standard deviation of the population divided by the square root of N. Okay, so if we do this, you get 0.045, which means that our standard deviation for our sample is, the variability is less. Okay, as expected, there is less variability in the distribution of a sample mean with N equals 20 than with N equals 5. Okay, so that's sample, and then this one, right? So here's the calculation. Suppose that a simple random sample of size N is drawn from a large population with mean mu and standard deviation, right? The sampling distribution of X bar will have mean X bar equal the mean of the population, right? The mean of the X bar is the same as the mean of the population, right? Those are going to be the same, but the standard deviation for the X bar is going to be the standard deviation of the population divided by the square root of N. Okay, so that right there is what we're going to have to understand, is these two things right here. Okay, the standard deviation of sampling distribution of X bar is called the standard error of the mean, and it's denoted by standard deviation of X bar. So it's the variability. So the shape of a sampling distribution of X bar, if X is normal, right? If a random X variable X is normally distributed, the sampling distribution of the sample mean X is normally distributed. So let's kind of look at that, right? So we're looking at this problem, right? This is this example 3 describing the distribution of the sample mean of the pennies, right? The weights of the pennies minted after 1892. It's we kind of grabbed that, but not looked at certain calculations on that as we've kind of progressed. So we're going to look at some calculations. So the weights of the pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02. So the mean, the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465, right? That's what we were supposed to, right? That's the sample mean is the same as the mean of the population, or the mean of X bar, right? 2.46, right? Now, the standard deviation of that is 0.02, right? divided by the square root of 10, which gives you 0.0063. That's the standard deviation. So Z is going to be, it says we obtain a sample mean of at least 2.465. So 2.465 minus, so ZEB is going to be, the calculation for ZEB is going to be X bar minus the mean of X bar over the standard deviation of X bar, right? So when we do that, it's going to be 0.079. And when you look it up on a normal distribution, this is the area that's going to give you, right? Right here. So we don't need that. So that's going to give us a 0.7852 if we would look it up on the table. But we're going to 1 minus that because we're looking, then it says at least, right? At least 2.465. Then we need what's above it. And that comes out to be 0.2148, right? And this is all done by looking at the table. And then 1 minus that, right? In the table, you're going to get this for this particular value, right? You do 0.7, and then you go out here to the 9, and that's where that table value is, right? So, and you 1 minus gives you that. So you got a 21.48% probability that we will obtain a sample mean, or that a penny minute after 1982 would be at least 2.465 grams, right? Is basically what it's saying. It's 21.48% that's going to happen. So, how do we do that with a calculator? Well, we're going to get to it on the calculator, I can promise you. And it's going to be a normal CDF, right? It's going to be a normal CDF. So, because we're looking at a lower and an upper, a mean and a standard deviation, right? So it's going to be a normal cumulative distribution function. And you can do that on that and get it, right? If you do that, that happens to be, make sure this is, okay, so a normal CDF, right? So we'll do my parentheses here. So the lowest value will be what? What would it be right here? At least this, right? So it'd be 2.465. And then the highest number would be E99. And then we'd have a mean of 2.46. And then a standard deviation of 0.0063. And if you do that, you'll get, guess what? Something very close to that. Okay. So these are the mean. It's kind of leavy. The mean of the X bar of the sample is the mean of the population, and then we calculated the standard deviation of X bar or the standard deviation of the sample. Okay, so really the only calculation you have to do is the standard deviation X bar, and then plug it into the computer, not computer, your calculator, and depend on whether it's below it or upper, your upper and lower bound type stuff. This is not a normal population distribution. Is not normal. The reason why, it's got a uniform probability, meaning every chance, every particular thing has the same probability of happening. So we couldn't do that, right? We couldn't do a sample means on that. So this one is an N of 4. The sample is 4, and this is 10, and then this is 30. So you kind of see how it's kind of, here's your histogram, right? These two bars over here are kind of jetted down, kind of lower, and that's with a sample of 4. But when we go to 10, this lower one drops, and this one kind of comes up, stays, and it kind of tends to be like a normal curve, right? And then when you get to 30, when your sample size goes up, increases, then you really get to a normal distribution. Okay, so the key to this is when you're doing sampling, you need to make sure that your sampling has a number that's high enough so that when you do different probabilities, different analysis on it, then you're really can look at it in terms of a normal approximation. Whether it's still skewed left or skewed right, it'll still take that normal shape, okay, which is going to be helpful in things later chapters to come, okay. And we've looked at that. We've looked, I think, in chapter 6, right? We looked at it in terms of binomial probability. If you increase the sample, then or the trials, the binomial probability, the histogram tends to become more normal shape, right? Go back and look at that. The mean of the sample distribution is equal to the mean of the parent population, right? We said that, the sampling distribution, the mean of that is equal to that. And the standard deviation of the sample distribution of the sample mean is the standard deviation of the population over the square root of n, right? Regardless of the sample size. You have to do this calculation to get the standard deviation of the sample, right? And that's x bar, right? Now, the shape of the distribution of the sample mean becomes approximately normal as the size of n increases. That's really theoretical stuff. You need to make sure you know that because it may ask you that, regardless of the shape of the underlying population. So that population can kind of be like really not a true normal curve, right? But the sample mean allows you to take that and make it more normally distributed. That's its whole process, its whole key focus on, okay? All right, let's look at this, the central limit theorem. We're going to kind of touch on this, but it's a really important theorem, but you could have a lesson in itself, but we're just going to kind of hit it for right now, just so you can understand some things. Regardless of the shape of the underlying population, the sample distribution of x bar becomes approximately normal as the sample size n increases, right? That's what we just talked about. Suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes, right? The mean of it. And with a standard deviation of 3.2. That's the standard deviation of the population. That's the mean of the population, right? 11.4 is the mean population. This is standard deviation population. If a random sample of 35 oil changes is selected, describe the sampling distribution of the sample mean, right? We're looking at the distribution of the sample mean. So solution, x bar is approximately normally distributed, right? So we have a mean of 11.4. So the mean of the sample distribution of the sample mean is equal to the mean of the population. But the standard deviation is going to be the populations divided by the square root of n, and n happened to be, guess what? 35, right? So we could take this, right? And we could turn around and we could do that, right? In our calculator, right? If a random sample of n's 35 changes is selected, what's the probability that mean oil change is less than 11 minutes, right? If it's less than 11 minutes, well, that's everything up to 11, right? So if we were to do this as a normal CDF, right, we'd have -1 E 99 11, right? And then we'd have the mean, and the mean happens to be 11.4, and the standard deviation of the x bar, right, of the sample mean would be 0.5409. And I'm just going to type that in real quick on mine, sitting here, not on the screen here. You should get the same thing. 11, and we're doing 11.4.5409. Yep. Paste, boom. And you get 20.2298, right? If you type that in, you get 0.2298, which is, if you do it by the table and you look at it, you're getting 0.23, right? So again, I like the calculator doing this. It's a lot easier. You don't have to go look at a table. You don't have to do this calculation right here. All right, but it does exist, and we have went through it, so there. All right. So that's really the lesson. This next part is all of the I shouldn't say all the homework. It's a couple of the homework problems that you'll see. Okay. So determine the mean of X bar and the standard deviation X bar for given parameters. If the mean of the population is 89, well, guess what? The mean of the X bar, the sample mean, is 89. The standard deviation X bar, the sample mean, well, that's really a calculation, right? X equals n over, not n, that's population over square root of n, right? So we said that that was 21, and there's n is 49, so that is the square root of 49. So we've got 21 over 7, which is, guess what? 3, right? So that's how that is calculated. Okay, so you've got to have those two things. Those two things you got to understand. The mean of the X bar is the same as the means of the sample mean, right? Those are the same. You've got to find the standard deviation of the X bar of the sample mean, right? And that's this calculation right here. So you've got to know that. So if there's something I would put down, that's it. Those two things right there, okay? Any questions on that thus far? Anybody? A lot of this is like, okay, so what are we really doing? Why we're doing this and everything? So let's kind of look at the problems itself, because it's regular chug and plug. So suppose a simple random sample of size n equals 64 is obtained from a population with a mean of 73 and a standard deviation of 16, right? So if we turn around and do a sample size from something that we already know what the data is, right, the mean and standard deviation, then we can really find the probability of something happening, right? Probability of the sample mean. How does that correlate back to the whole population? It should be a 1-for-1, right? So because it's normally distributed. So we're going to go through, we're going to describe the sampling distribution of X bar. We're going to calculate probability of X is greater than 75.7. We'll do a probability of X is less than or equal to 69, and then we'll do what the probability is from 71.8 up to 76.9, right? So those are all B, C, and D on this parameters using the given information. So the first thing that we got to do is the mean of the X bar is equal to the mean of the population, so that's 73, right? The standard deviation of X bar, right, is equal to the standard deviation over the square root of n, and n is 64. So guys, we got 16 divided by 8, which the standard deviation of that is 2, right? Standard deviation of X bar is 2. So choose the correct description of the shape of a sampling distribution of X bar. Well, first off, it should be what? The distribution of that sample mean should be approximately normal, right? That's what we show. No matter what the population curve looks like, if we're looking at the sample mean of it, right, of the sample, then we can normalize it, right? So it's approximately normal. So find the mean and standard deviation of the X bar, boom, right? Done those two calculations, right? So that's part A, just that portion of it, okay? Any questions on that? Anybody? All right. So the next part is the B, C, and D, right? So we've got to calculate that. So we can, Z is equal to the X minus the mean, right? So this happens to be, and I'm going to do this right here by hand. So 75.7 minus, and the mean is 73, all over standard deviation of the X, right, which happens to be 2. And when we do this, guys, we get 1.35. Now, if we go to a normal curve, right, and we look at 1.35, we get a Z of 0.0 9115, right? But that's for everything from here over, right? All of this. That's the area for all of that to the left, but we're needing to the area to the right, right? So what do? We do 1 minus 0.9115, and we get, guess what? 0.0885, which is, boom, what they got, right? So you could look at the normal table and pick out your value of 1.3, go all the way over to 5, it's 0.9115, right? So there. Now, you can do that by hand, and I encourage you to do it by hand. But we're also going to show you how to do this, okay? So you're going to do, this is B, so we're going to do the normal CDF, right, cumulative distribution function. We got a lower bound of, we're finding this, right, to the area to the left, 1e to the 99, all the way up to 75.7. Now we have a mean of 73, and then we have a standard deviation of x, of the sample mean of being 2, right? And when you do that, you're going to get an answer, which should be 0.09115. And of course, we want the area to the right, so it's this, right? Boom, there, which is 0.0885, right? You do 1 minus that answer that just popped up, and that's what we can do. So that's what we're going to do. Well, for sake of time, let's say 608, man. I may set some of these up, and you're going to have to do them, because I really need to get the parts E and F, because you're not going to know how to do that if I don't. So let me just show you how to set C and D up, right? So it's a normal CDF, right? This is everything below it, right? So when we do this, we're going to get that. The answer, the area underneath the curve, the probability of it, is going to be our answer, right? So we're going to have negative 1e, 99, comma, all the way up to 69. And then we'll have, what, 73 and 2. And ladies and gentlemen, that'll give me 0.0228 when you type that in your calculator, okay? And then if you do the between, right, the between, which is really the easiest one of every bit of them, because we're dealing with a lower bound and upper bound, right? So the lower bound happens to be 71.8. The upper bound happens to be 76.9, right? Our mean and our standard deviation of the sample mean does not change. Those are still that. And then, ladies and gentlemen, you get this. Well, actually, when you do it on a calculator, mine came out to be this, 2, right? This is what they want, but they'll take 3 answers, and then one of 3 answers based off the error of calculation, right? So it's in there, okay? Huh? No, ma'am. Why? Why do we not, Myra? Look at your parameters for D. Is it saying greater than or less than a certain point, like B and C did? Uh-uh. It's yeah, okay. It's saying between the 2 points, right? So the lower bound and right bound on that, okay? So just, yeah. So when you do D, note that you're going to be, you're going to get rid of your negative 1e to the 99, right? So you're going to have to know how to put that in. So go back and look at that. That's, to get the scientific notation, that's Sackett comma, right? Oh, no, no, you're right. It's 0.915. Not I typed it in. Yeah, I'm no, no, that's a good catch. That's a good catch. So that's I just I had it written out and just in the haste there. So that's why it's one minus that, which gives you that. So yeah, good catch. Thank you. All right, so let's look at the next problem because it's got A through F, and really this is the meat and taters. Okay, so what you're going to be doing this whole problem, the A, B, C, and D, right? The A is just looking at a certain parameter, right? Um, and we got to do some calculations that we're going to use. But really, what we're really looking at is just doing what happens to it as um, as the population or the sample size goes up, right? So, you know, we're going to be looking at the uh, standard deviation of X bar, right, of the sample mean, right? So when we're calculating this, um, it says what is the probability of a randomly selected student in a city will read more than 92 words per minute? Well, um, the reading speed of a second grade student in large cities is approximately normal, right? It's approximately normal, the curve of it, the population of it. So when we do the sample means of the population, then we're going to really normalize the curve, right? So the mean of that is 88 words per minute. So the mean of the population is going to be the mean of the sample mean, right? Mean of the X bar, right? Sample mean. And the standard deviation is 10 words per minute, right? So that's that is the standard deviation of the population. And I'm gonna put a P there, just so, well, I better not, because then because I didn't notate it like that on the other. I just said it. So that's really the standard deviation of the population, right? It's 10. So our first problem is, okay, if we're going to randomly select a student, right? So the N is, guess what? 1, right? Then we're going to have to find the standard deviation of the X bar, right? And that's going to be 10 over the square root of 1, which is, guess what? 10. So when you do this, you're going to, again, do a normal CDF, right? You're going to go, we're looking at it that the randomly selected student will read more than 92 words per minute, right? So our X, right, our lower bound, our X bar is really 92, right? So 92 is we'll read more than that. So 1E, 99. And then we're going to put what? The mean of that's 88, right? So 88, and then we'll put 10. And when you do that, you should get 0.3446, right? Which really is 34.46%, right? So that's why, you know, round it off to the nearest percent for the interpret the probability. If 100 students were chosen from this population, we would expect 34 of them to read more than 92 words per minute. Now, why 100? Because we're dealing with this as a, guess what, a percent, right? And if you have 100, each one is, you know, each, we can, 100, each one would be, if you think about it, 1%, right? So that's why they did it with a, you know, if 100 different samples of students were chosen, then we could look at it from individual percents. All right. So if we do this, we do part B, what's the probability of a random sample of 11 second grade students? Okay, the only thing that's going to change is this. We got to find the standard deviation of X, which would be, guess what? Standard deviation of the population over the square root of 11. Well, guys, that comes out to be, and go out to 4 decimal places, right? Is going to be 2.1320. Now, we need to finish this the sentence because we need to find out what our X bar is. So we got our N is equal to 11, right? So second grade students from the city result in a mean reading of more than 92, right? More than 92. So we know it's above 92. 92 is going to be the limit or the lower limit, right? So a normal cumulative distribution function. So 92, comma, 1E, 99, comma, 88, and then look at this. 2.1320, that's the new standard deviation of the sample mean, right? That's going to give us, guess what? 0.09, no, that's, yeah, sorry, 0.0923, which is 9.23%, which is, guess what? That's why that 9 is there, right? If 100 different samples we were chosen, we expect 9 students, right, to be able to have a sample mean reading rate of more than 92 words per minute. Okay, does everybody understand how the verbiage here is tying into what we're finding? So that's really 9.23% probability that they'll have a rate more than 92 words per minute. And if you're doing a sampling in of 100 different samples of N of 11, right, 100 different samples, then we can say 9 students. We would expect 9 students to be that way, right? So it makes our math a little bit easier from telling what does that 9.23% mean. Well, if you do 100 of them, then you're talking about 9 students. And the previous one, we had 34.46%, so we would expect 34 kids on that one. Now, it's going to do it again, but on this time, we're looking at a sample size of, guess what, guys? 22. N is 22, right? So our new standard deviation of X bar equals of the sample means, right, is going to be 10 over the square root of 22, which is, guess what? Let me go back because I think I made a mistake right here on this one. It won't be that. I copied error. Sorry. Copy error. Copy this, copy this, copy this. Because if you type that in, let me fix that. That should be 3.0151, and this should be 3.0151. Okay. So make that correction on your notes for that one that had a sample size of 11. I grabbed the wrong standard deviation for it. So this is the one for the 22, right? So we do this now, normal CDF, right, is of more than 92, again, 92, 1E. All we're doing is increasing our sample size, right? Again, that's 88, and we've got 2.1320. And then we would get this, 0.03. Okay. Which is really 3.03%, right? That goes with this. That's why that right here is a 3. So if we were to take 22, we would expect 3%, 100 samples of 22 students sampled, right? Then we would expect 3 of them to have a sample mean reading rate greater than 92. All right. So what effect does increasing the sample size of the probability do? Well, increasing the sample size decreases the standard deviation, right? And if you looked at that, because it's the standard deviation of the sample mean is the standard deviation of the population divided by the square root of N, right? So as your N gets bigger, that's going to make that get smaller, right? It's just the way it works from a denominator standpoint. So just kind of know that. That's really where they're going on this problem. I'm going to finish up this E, and then we'll look at F, because they're giving it to you and it's not intuitive. Okay, so we're looking at this. A teacher instituted a new reading program. And after 10 weeks, the program found that the reading speed of the random sample of 18 second grade was 90.7, right? 90.7. So with what might you conclude based on this result? Select the choice below. So we need to see, is this new change, is it better or is it worse, right? So we've got an n equals 18, right? The let's see, the mean of the still of it of x bar is still 88, right? So we need to find the standard deviation of the x bar, and we've got 10, right? Because that's the 10 over the square root of 18, and that's going to give us I'm not sure what that's going to give us because I just left it in it. So let me see what that is. 10 divided by the square root of 18, so that you at least have a number, and that's going to be 2.357, right? So we're going to do a normal CDF, right? Because we want to know that a sample of 18, right? And that the a random sample of 18 second grade students was 90.7, right? What might you conclude about this? Is it greater? Is it, what is it, right? And you either got A or B. A mean reading rate of 90.7 is not unusual or it is unusual, but since the probability of obtaining a result of 90.7 words per minute or more, so we're looking at a lower limit of, guess what? If it's 90.7 or more, our lower limit is 90.7, right? Our upper limit is E99, and then we've got 88, which is our sample mean, right? It's the same as population mean. And then you can put 2.357, right? And when you do that, you get, guess what? 0.1260, which is 12.6%, right? So that's where that comes from, right? And then if you round that, that's really 12.63, 12.6% rounds up to the nearest whole number, which would be 13, right? Because it's the percentage 12.6 is greater than 5, right? Because it's greater than 5, then we would not say that it's unusual, meaning we would expect that to happen. If it was below 5, then it would be an unusual probability, which we would expect it not to happen. Okay, the probability that's unusual, it's probably not going to happen, right? So that's what they're talking about, usual and unusual. That we looked at that in a previous section. All right, so the last one, F, which is really the hardest one of it. It's not too bad, but I mean, you got to look at it. There's a 5% chance that the mean reading speed of a random sample of 23 second grade students will exceed what value, right? So we're looking at this 5% chance, right? Well, it's a 5% chance. I mean, hold on. Because there's nobody in here with me, and I'm the only one, the sensor itself kind of went off. So let's kind of look at this. So our N is 23. We got to look at our P and Q, because this 5% chance is actually an area, right? So it's an area. So we're going to do what's called an inverse norm, right? Inverse norm, right? I think it's number 3. And if you think about it, it wants P, which would be 0.95, and then the Q is 0.05, right? There's a 5% chance that will happen, not, so there's 95% chance that of success that the kids will have a random speed that will not exceed, right? So anyway, so you do that, the inverse norm, you need a p-value, right? You need a p-value of success, right? 95. And then you need the mean, x bar, and then you also need, guess what? Standard deviation of x bar. And when you do that, the standard deviation on here of x bar, it is 10 over the square root of 23, right? And I just typed that in as 10 square root of 23 in my calculator, but I didn't give it as a decimal. I just typed it in when I did it on the probability, right? When I do that, that actually is 2.0851. And of course, when we do this, the inverse norm, that'd be 0.95. So we're wanting, now why did I, when it says exceed, if it's, okay, so we're looking at this would be the area of 0.05. So we're needing this area over here, okay? We're needing this probably, and that's 0.95. That's why I made this P be 0.95 and not 0.05. Do you understand? We're wanting to know that, you know, what is it going to be? So 0.95 and then 88, and then of course that becomes 2, that's 8 there, 2.0851. And when you do that, ladies and gentlemen, you get a 91.4298, which is, if you go to 2 decimal places, is 91.43, right? Okay. And it's not 2. So 91.43 words per minute, right? So there's 5% chance that the mean reading speed of a random sample of 23 second graders will exceed 91 point, right? So there. That's it. That's all I got for you, folks. I know I went over my time and everything, but there. Yeah, if I look at that, that's actually, this would be 0.95 and this would be the 0.05 up here. And we're needing that. So that's why that. The area to the left is what the inverse norm is going to give us. Okay, so there. All right, any questions? That's a whole lot on 8.1. We still got 8.2 to do in that and stuff like that as well. Okay, so